Try and float an egg in water, then dissolve salt in the water until the egg floats. How does the density of an egg compare to that of tap water? To that of salt water. So this one is a regular water and the egg would sink to the bottom. And this one has a lot of salt water in it to where this egg will actually float on top. Or just bob right there. And the reason for this is because the solution is denser than the egg itself. So when you put the water in it, it makes the water more dense to where the egg won't drop. In this one, we punched a couple of holes in the bottom of a can. And this one, it says, punch the holes in the bottom of a water-filled container and water spurts out because of the water pressure. Now drop the container as it freely falls. Note that the water no longer spurts out. If your friends don't understand this, explain to them why. So the water would empty out, and as you drop it, it should kind of stop before it hits the bottom. And that is because the water in the bottle are both falling to earth They're falling at the same rate downward to the earth's gravity, so the water doesn't even have the chance to leak out. It's already taken the easiest route down. Place a wet ping pong ball and a can of water held high above your head and then drop the can on the rigid floor. Because of the surface tension, the ball is pulled underneath the surface as the can falls. What happens when the can comes to a complete stop? It's worth watching is what it says, but we can't drop it too high. But the idea is that it sucks itself under, and then when it stops, the momentum pushes the ball back up, just like that. So it would pop it out like that. This says try this in a bathtub. We're going to do it in the sink. When you are washing dishes, take a glass, mouth down, over a small floating object, a ping pong ball. What do you observe? How deep must the glass be pushed in order to compress the enclosed air to half its volume? You won't be able to do this in your bathtub unless it's 10.3 meters deep, and I don't think any bathtub's that deep. So you just push it on top of it and go all the way to the bottom, and it'll just roll on the bottom because there's no water in there. Compare the pressure exerted by the tires of your car on the road with air pressure in the tires. For this project, you will need to obtain your car's weight, which my truck was 4,500 pounds, and I divided that by 4, and that equals 1,125 pounds. Supported by each tire. You can closely approximate the area of contact between a sheet of paper marked with 1-inch tire or 1-inch squares beneath the tire. Are they nearly equal? Which one is greater? I couldn't do this one because my truck tires were too big. I have big mud tires, so I wasn't able to do this experiment. But I think the weight supported would be greater. You ordinarily pour water from a full glass into an empty glass simply by placing the full glass above the empty glass and tipping. Have you ever poured air from one glass to another glass? This procedure is when you take one glass, you can fill this one up with water so you can see the air actually go inside of it, and then you just basically turn this up and air will enter this one instead of this one. Raise a filled glass of water above the water line, but with its mouth beneath the surface. Why does the water not flow out? How tall would the glass have to be before the water began falling out? So we kind of just did that one with the other one, where you fill it up with water and then pick it up, and you can actually put it all the way to the water line without the water falling out until you lift it above the water line. So until you lift it above the water line, the water will stay in there, just due to no air being able to come in or out because it's all water. Place a card on top of an open glass filled to the brim with water and invert. Why does the card stay in place? So this one, we would fill this almost all the way to the brim And then I have this piece of cardboard as my card. Oop, a little bit fell out. And then take it over to the sink. Flip it upside down. And it creates a seal and kind of a suction. I don't have a glass, so it's kind of hard to do sideways, but it'll just kind of stick there until you take it off. This is because the adhesion occurs because water molecules having the positive and negative ends are also attached to the other materials. The water molecules are attached to the paper, adhering to it while continuing surface tension with other molecules. The note card does not fall due to the direct differences in pressure and does not slide because of the surface tension. Invert a water-filled soft drink bottle or a small neck jar. Notice that the water doesn't simply fall out, but instead gurgles out of the container. Air pressure doesn't allow the water until some air has pushed its way up inside the bottle to occupy the space above. The liquid. How would inverted water-filled bottle pour out if you tried this on the moon? And I would assume, wait, no, I'm using this bottle. It's already got water. So when it means gurgle, it's not gonna come out smooth, but a trick, you can just kind of swirl it and it'll come out like that. And my assumption would be that the little air pressure on the moon would allow the water to flow out much faster, almost like a vacuum. But realistically, the moon's super cold, so the water would probably freeze before you started pouring it out. Pour about a quart. I can't do this one, this experiment, because I don't have the container large enough to do it or the place to do it with. So you would pour boiling water inside of a gallon or 5-liter metal can with a screw on top. Place the can open on a stove, and then when it starts to steam, you would put the cap on quickly and then set it aside. And as the steam inside cools, it would compress the can, causing it to shrink. And we can do the same thing in a smaller scale with a can and ice water. I'm gonna fill this with ice now. And we can pour that into this. Some boiling water. That's kind of hot.
Here.
And then we would just invert it inside of this. And kind of, hopefully it kind of shrunk a little bit with the sides. But it's supposed to shrink in because of the hot steam inside is condensed because of the cold water, causing there to be less air pressure, shrinking it. So it kind of did it on the sides a little bit, but not as much as I wanted it to. The next one is make a small hole near the bottom of a can or bottle filled with water as it proceeds to spurt out of the hole. If you cover the opening at the top, the water stops. Explain. So with this one, you can fill this thing all the way up, and I have holes already pre-cut, and it kind of just drops. And if I put my hand on top or screw on the top, it'll actually stop leaking, just like that. And this is because when you cover the top, air cannot get in to fill the empty space. The air pressure inside of the bottle drops a little. The higher the air pressure inside the bottle drops, oh wait, I kind of messed up my writing. The higher air pressure arm around the bottle pushes against the holes in the bottom of the bottle. This stops any more water from escaping. The surface tension at the bottom of the water bottle kind of creates a seal on the holes as well. Lower a narrow glass tube or drinking straw into water and place your finger over the top. Lift the straw and see what happens when you lift your finger. So this is just a kind of a suction trick to where you can pick up the water with a straw and then it'll collect it inside, which is pretty cool. Push a pin through a small card and place it over the hole of a thread spool. Try to blow the card from the spool by blowing through the hole. Try in all directions. So it says to put, I already pre-punched a hole, put it through a spool of thread, and then it says to blow, but nothing really happens. I don't know if I'm doing it right or if I read the directions wrong, but I don't know what's supposed to happen. I looked it up and I couldn't find anything. So that's that experiment. Hold a spoon to a stream of the water, sink, and feel the effects of difference in pressure. So you take a spoon, and as you put it on the water stream, it kind of sucks it into it. If you hold it by 2 fingers, it just kind of sucks it onto the stream, which I find pretty interesting. Write a letter to your grandparents telling them what you're learning. So I would say, Dear Nana, I'm taking a physical science class in the summer. Did you know that boiling water actually is a cooling process? Boiling is a rapid vaporization of a liquid, which occurs when a liquid is heated to its boiling point. The temperature at which the vapor pressure of the liquid is equal to the pressure entered on the liquid by the surrounding atmosphere. Maybe you could tell this to one of your friends as you're making tea. Do as Megan shows in figure 7.7 and blow on your hand, first with your mouth wide open, then with your lips puckered, so that the air expands when hitting your hand. Account for the few temperature differences. So as you open your mouth wide, it's going to feel more hot, and if you pucker your lips, it's going to feel more of a cold. But if you pucker your lips and put it close to your mouth, or close to your hand, it's still going to be warm. When gas expands, it cools. So having a small opening in your mouth allows the air to expand as it leaves, leaving increases in the volume rapidly and thus also decreasing the temperature of the air. If you live where there is snow, which we don't, we're in Georgia, do as Benjamin Franklin did more than 200 years ago. Lay samples of light and dark cloth on the snow and note the differences among the rate of melting beneath the samples of cloth. And we know that lighter cloth reflects sunlight, so it would reflect the sunlight off of the cloth, leaving the snow less melted than if you put a black cloth in the sun. The black cloth will absorb the sunlight and make the snow melt faster. Hold the bottom end of a test tube. We can't do this one either. I don't have a test tube or a concentrated flame that would boil water in a small concentrated area. Hold the bottom of a test tube and full of cold water in your hands. Heat up the top in a flame until the water boils. That you can still hold the bottom shows the water, as well as glass, is a poor conductor of heat. This is even more dramatic when you wedge chunks of ice between steel wool at the bottom. Then the water above can be brought to a boil without melting the ice. Try and see. I wish I could. 35. Wrap a piece of paper around a thick metal bar and place the flame. Note that the paper does not catch fire. Can you explain why? I could not find any metal bars thick enough to do this experiment at Walmart, but I do know why it happens. In order to burn anything, it needs to reach a certain temperature or a flash point. If the paper is close enough in contact with the heat sink or the metal in this case, then the heat will be withdrawn from the paper very quickly, and quite intense flame would be needed to burn that paper. So the bar just soaks up all the heat before the paper can catch fire. I don't have a Pyrex funnel to do this either. I don't have a lot of this stuff. Pyrex funnel, mouth down in a saucepan full of water in such a way that the straight up tube of the funnel protrudes out of the water. The rest of the part of the funnel, put a coin underneath the funnel so that the water can get underneath. Place a pan on the stove and observe the water as it begins to boil. Where do the bubbles form first? Why? As the bubbles rise, they expand rapidly and push the water ahead of them. The funnel confines the water, which is forced up the tube and driven out at the top. Now do you know how a geyser or coffee percolator works? So how a geyser works would be a magma changer provides heat which radiates around surrounding rocks. Water from rain and snow works its way through the cracks underground and fractures in the rocks. As heated water nears the surface, the temperature drops and the water flashes up and make steam that comes into a geyser. Observe the spout of a tea kettle. I don't have a tea kettle or a candle because we're not allowed to have candles in the dorms. Observe the spout of a tea kettle, boiling water. Notice that you cannot see the steam that issues from the spout at the cloud. You can see further away from the spout that this is steam, but condensed water droplets. Now hold the flame of a candle in the cloud of condensed steam. Can you explain your observation? I don't know what would happen, but I would assume a bunch of little tiny water droplets would push out the flame due to like the air from the protrusion of it and the water itself. You can actually make rain in your kitchen. Put a cup of water in a Pyrex saucer pan and heat slowly with a low flame. When the water is warm, place a saucer on top filled with ice, and as the ice melts, water droplets will form at the bottom of the saucer and combine until they are large enough to drop, producing a steady rainfall. And this is the same way it works in the clouds. They form up and get together and bigger until they're heavy enough to drop out of the clouds. So it kind of works the same way, which is kind of cool. Suspend a open top container of water in a pan of boiling water which is topped above the surface of the boiling water. You'll note that although water in the inner container can reach 100 degrees Celsius, it cannot boil. Can you explain why? The boiling water needs not only to reach the boiling point, but also continually absorb heat. The water in the inner container wants to boil it can't boil because it can't get any more heat from the surrounding due to being in the same temperature as the other water. And that is the end of lab number 2. Thank you.